A rotating magnetic field. Majority of electrical machine operates at a rotating magnetic field. In fact, it is a running wave, the wave that runs in the A gap circumference. In real motors, the rotating magnetic field is generated by the stator winding. In this example, we will review the way to generate the rotating magnetic field with a boundary condition. It's a useful feature if you want to study the rotor behavior in an ideal sinusoidal magnetic field without high harmonics. In this model, we have the solid copper cylinder, an A gap, and the boundary condition where we are going to specify the running wave boundary condition. But first, let me explain what is the running wave. Take a look at this page. Here is the cosinusoidal wave, a function of phi, and phi is the coordinate along the A gap circumference. So far, it is a standing wave. It doesn't change in time. But if I add here the phase shift that depends on time, this wave becomes a running wave. If I change the time, you will see that the wave is moving. Okay, let's start QuickField now. In QuickField, I create new problem, rotor. Next, problem type is transient magnetics. Every simulated device is a three-dimensional object. I'm going to simulate only a single cross-section, so the model class is two-dimensional plane parallel. Length units are millimeters. Next. Here I should specify the integration time. Let it be 0.1 second. And I'm going to use the automatic timestamps. Finish. On the left, you can see the problem pane, and on the right is the geometry model editor window. You can draw the geometry model here, or you can import the geometry model from the AutoCAD Excel file. The model is simple, so I'm going to draw it here from scratch. First, I will insert a shape, a circle, with a diameter of 50 millimeters. Insert, and another circle with a diameter of 40 millimeters. Insert, close, zoom to fit. Here you can recognize rotor, A gap, and external boundary. Let's assign labels. Through labels, we will explain the geometric object's meaning and provide material properties. Switch to Select Objects mode, click to select, and type in the label name here. This is rotor, this is air, and these edges are boundary. Hold the Ctrl button pressed to select multiple objects at the same time. Okay. So far, these are just text labels. Now let's provide physical properties for the labels. Double-click the label name in the tree. Relative magnetic permeability of the air is 1. Okay. Rotor is made of copper. Relative magnetic permeability is 1. And the electrical conductivity is 63 megasiemens per meter. Okay. And for the boundary, I will specify the tangential magnetic field, and I will simply copy the formula from the website. Copy. paste. Here, phi is the angle, and the multiply defines number of poles pairs. Let it be one pole pair. Okay. The time multiply defines the rotation speed. One turn is 360 degrees. That is, in 1 second we make a one turn. If you have a 60 Hz, then you should multiply this by 60. And the magnitude defines the flux density value. Let it be, for example, 100,000 amperes per meter. Geometry model and the data are ready. Before I start the analysis, I should build the finite element mesh. Just press this button and the mesh will be generated. Now save all problem files and run the analysis. The problem has been solved. Let's take a look at the results. Here are the results. You can see the field lines and a color map of the current density in the rotor in the final moment of time. You can rewind to the initial moment of time, or you can choose any intermediate time layer. You can switch the animation on. Now let's check some parameters. You see there are eddy currents in the rotor. The total current should be 0, but the joule heating is not 0. Okay, I will use the contour tool. Click to select the rotor. Open the integral calculator. Here you calculate the total current, 0. And you can calculate the joule heat, and you can calculate the torque. These values are calculated per 1 meter of the rotor length, and these values are calculated for that specific moment of time. You can see how value changed in time. Right click, time plot. And the exact values you can see in the timetable. You can also use contour to make an XY plot. Here I will clear the contour, change the line type to be the half arc, and draw the contour in the A gap. Contour close, contour change direction. Now let's take a look at the flux density distribution in the A gap. Open the XY plot. Here I will change the value to the flux density normal component. Again, this is the flux density distribution for the specific moment of time. If you change the time, you will see that the wave is running. If you search for the rotating magnetic field on our website, you will find the example page. Here you can read about problem setup, browse the solution section, take a look at the resulting pictures, and download the simulation files. Simulation files may be opened and the results may be viewed using any QuickField edition, including QuickField Student Edition that you can download from our website for free.